This is a demo to show how to design a mutagenic primer to introduce human C333F mutation into yeast MSH2 gene. The link of the protocol is highlighted in the URL window. There is a tutorial on the principle. There is also a tutorial to explain the cognate site, basically how to find out the human and yeast cognate site. And now let's follow in this exercise. And first you can find out the human and yeast protein MSH2 sequences in a FASTA format from a link in the protocol. Once you got the sequence, you highlight the yeast SC MSH2 for Saccharomyces cerevisiae MSH2, HS MSH2 for Homo sapien MSH2, and score 1, that means isoform 1. So edit, copy, and then we can Google EMBL cluster W2. It's going to give you the multiple sequence alignment software cluster W2. Then in a window, we paste the sequence. Okay, that's the sequences. Let me submit this one. And then it's going to generate an alignment. And you can also show color. So what this alignment is, you can see in the first 1 to 60, the sequence are perfectly aligned. Well, they are also the 1-to-1 correspondence. So for the 60th position in yeast, you also see the same position in human, 60-60. But then you will see human MSH2 have 2 deletion here, while the yeast, or you can say the yeast has 2 insertion here, N and C. And then you see the L and M are also corresponding sequences in human and the yeast, but then their position, their numbering will be not the same anymore. Right, so this is 60, then you have 61, 62. So let me use a pen. Blue. Okay, blue is fine. Okay. Oh, gee. So this should be 1, 2, 3, 4, 5. Right, so then the yeast have 2 extras. Right? N and C is extra, so 6, 7, 8. So this will be for the L here, this will be 69 in yeast. At the bottom, this one in human, this should be 67 because it's missing these 2. So this will be 1, 2, 3, 4, 5, 6, 7. Sorry, bottom M. So they're starting here. The yeast and human, their numbering will be different, but their position is still the same. So for example, N and N is here. The same principle, which is like if you can think about every street, right? Every street, let's say there are some horizontal street. There are houses on each street. Right, there are houses on street. In theory, we can also align those houses and then find out their corresponding position. If I say well, there is a one. Let's say in each house, in each street, there is a one of the a red house. It's actually blue. Sorry. But their numbering may not be the same. Let's say this one is the 1502, this one is 1504. In this street is 2002. This is 2004. Right. So these two houses are we can call that coordinate site, but their numbering are not the same. Okay. And we come back to the human and yeast alignment again. So for the human C333, we found it here. So that's a human C333. In yeast, it's also a C cysteine, but the yeast position is 345. That's really the key. But so 345, if we want to go back to find out the codon position, remember each codon is 3 nucleotides, so we have times 3. So that would be 5, 3. Right, so that's 1035 position in codon. But each codon has 3 nucleotides, so this will be from position 1032 to 1035. That's the position we're going to look for in the codon position. And let's go back to the protocol again. So then that's alignment. We found out that the 333 corresponding to yeast 345. And then now here's the thing. We want to change the position from cysteine to phenylalanine F. The F, if we look at the genetic codon in yeast, we found out the F can be encoded by TTT and TTC. That's the F. But then you will see the 0.059. That's a frequency of the TTT being used by yeast. So TTT is used by 59% codon. This is called a preference preferred codon in yeast. In general, this is also something called a codon bias. So apparently, all codon are not all the same. Some codon are used more often than a species to other codons. And those most frequently used codon is called a preferred codon. Is also because there are more tRNA carrying this anticodon more abundantly, and the incorporation of this of this codon into the mRNA will be more efficient and less error prone. It will be more accurate. So for yeast, this is TTT, the preferred codon for FATTT. The position actually should be 1033 to 1035 because you have to miss one position. So I think I made a mistake in the PowerPoint slide. So this shouldn't be 1032, this should be 1033. Sorry. That's okay, I made a mistake on the slide. Okay. And then let's see, we just have to find out this position using APE. So this is the yeast open reading frame, and we can again copy these sequences. Okay, edit, copy, and go to APE and paste these sequences there. Oh, let me see. Edit, paste. Oh, I have to save this one. So this is yeast MSH2 APE. Okay. And we need to edit, select from 1033 to 1035. That's original codon is TGC. We need to change this to TTT. So the original codon is TGC. We change that to TTT, and then now the primer. To design a primer, we are going to pick 10 base pair to the 5' of these sequences, and then 10 base pair to the 3' of this base pair. So basically, well, this codon position is 1033 to 1035, and to the 10 to the left will be 1023. 10 to the right will be 1045. So we're going to select from 1023 to 1025. So edit select from 1023, 1025. And then I say copy, file, new file, that's the mutagenic primer. And in the middle, they should be TTT. Oh, I did a little off the protocol. The protocol actually changed the nuclei afterwards. I changed it before, but it's the same thing. Okay, but you have to keep your mind clear where you change it. So.